The electrical resistance of copper-thin films depends on the thickness and temperature of the films. Generally, the thinner the film, the higher the resistance, and the higher the temperature, the lower the resistance. The electrical resistance of copper-thin films can be calculated by the following formula. R equals ρ, A/L. Where R is the resistance, ρ is the resistivity of copper, L is the length of the film, and A is the cross-sectional area of the film. The resistivity of copper is about 1.68 times 10 to the power of minus 8 ohm m, at room temperature and varies with temperature. When the thickness of copper-thin films becomes very thin, the resistivity increases and the electron-phonon coupling constant increases, resulting in a higher temperature dependence of resistance. Therefore, it cannot be concluded that copper-thin films have lower resistance than thick copper. Rather, it may be the opposite. The electrical resistance of copper changes depending on the temperature, and generally, the higher the temperature, the higher the resistance. This is because the resistivity of copper increases with temperature. The resistivity of copper can be expressed by the following formula: ρ equals ρ0 1 plus alpha, T minus T0, where ρ is the resistivity. ρ0 is the resistivity at the reference temperature, T0, alpha is the temperature coefficient of resistance, and T is the current temperature. The temperature coefficient of resistance of copper is about 0.00393 K to the power of minus 1, and the resistivity at room temperature is about 1.68 times 10 to the power of minus 8 ohm m3. Therefore, the electrical resistance of copper can be calculated as follows. R equals R01 plus alpha, T minus T0, where R is the electrical resistance, and R0 is the electrical resistance at the reference temperature T0. For example, if the length of a copper wire is 10 meters and the cross-sectional area is 2 times 10 to the power of minus 6 and the reference temperature is 20 degrees Celsius, the electrical resistance can be obtained as follows. R0 equals ρ0 A/L equals 0.084 ohms. If the current temperature is 50 degrees Celsius, then the electrical resistance changes as follows. R equals R01 plus alpha, T minus T0 equals 0.084 ohms times 1 plus 0.00393 times 50 minus 20 equals 0.0965 ohms. That is, if the temperature rises by 30 degrees Celsius, the electrical resistance increases by about 15%. The electrical resistance of a thin film depends on its thickness and temperature. Generally, the thinner the film, the higher the resistance, and the higher the temperature, the lower the resistance. However, this only applies when the film is not very thin. When the film becomes very thin, the non-resistivity increases and the electron-phonon coupling constant increases, resulting in a higher temperature dependence of the resistance. Therefore, it is not possible to conclude that copper topped in a thin film form has a lower electrical resistance than copper in a thick form. It may be the opposite. In other words, the electrical resistance of copper varies depending on the temperature and thickness, so you need to distinguish between general rules and exceptional cases.